Our next example uses a deck of cards. If you need some hints, you can always refer to the notes on the previous page. You were dealt one card from a standard 52 card deck. Find the probability of being dealt the following. Well, before we start any of these problems, we need to know what n of the sample space is. Because there's 52 cards in the deck, n of s is 52. Now we're going to try to find the probability of drawing a queen. So how many different queens are there in our 52 card deck? Well, we have 4 queens, one of each suit. So therefore the probability of drawing a queen is equal to the number of queens over the number of sample space, which is 4 over 52. Now if you take 4 over 52 and reduce it, you get 1/13. So the probability of drawing a queen is 1 out of 13. For our next, we're looking for the probability of drawing a heart. So how many hearts are you going to have in your 52 card deck? Well, it turns out that there's 13 hearts, so the probability of drawing a heart is equal to the number of hearts, which is 13, over my sample space, which is 52, and that reduces to a fourth. Next, we're looking for the probability of drawing the ace of spades. Well, if you look back on the deck of cards, you will notice that there's only one ace in the suit of spades. So there is only one ace of spades. So therefore, the probability of pulling that ace of spades is only one possibility out of the 52 card deck, and that doesn't reduce. Next, we're looking for drawing the probability of a 5 or a jack. So if you're looking for the number of 5s or jacks, you'll notice that we have 4 5s, one of each suit, and 4 jacks, one of each suit. So we have a total of 8 cards that are either a 5 or a jack. So therefore the probability of pulling a 5 or a jack is equal to 8 out of the 52. Now 8 out of 52, I can divide by 4, and that gets me 2/13. And our last one on this problem, probability of drawing a red card or a queen. Now this one's different than part D. Part D, you can't have a 5 or a jack. You can't be a 5 or a jack at the same time, right? Any card is either going to be a 5 or a jack or not either of those two things. But when we're talking about red or a queen, there are some queens that are red. So we need to be really careful about how many reds or queens we have. Okay, so let's think about this. I've got 26 red cards, of which 2 are queens already. So how many non-red queens do I have? Well, I have 2 black queens. So if I add the 26 red cards, which already include 2 of the queens, plus the 2 black queens, that gets me 28 cards that are either red or a queen. I just don't want to add 4 plus 26 because then I'm adding the queens twice. So I could use the union rule for sets, which says the number of red or queen is equal to the number of red plus the number of queen minus the number of the intersection, red and queen. So that would be, let's see, 26 plus the 4 queens minus the 2 overlaps. We're still going to get 28. So the number of red or queen is going to be 28. So the probability of red or queen is going to be 28 over the sample space, which is 52, and that reduces to 7/13 if you divide the top and the bottom both by 4. Our next example is an example for a family. You select a family of 3 children. If M represents a male child and F represents a female child, the set of equally likely outcomes for the child's genders are as follows. Your sample space would be male, 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 female, and so on and so forth. How many total choices do you have in the sample space? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different ways that you could have the 3 children being in different combinations of male and female. So find the probability of selecting a family with A, the probability of having exactly 1 female child. So what is the number of exactly 1 female? Well, if I'm just going to look up here, MMF has 1 female, MFM has 1 female, and FMM also has 1 female. All of the other choices have either more or less than 1 female. So that looks like my number of exactly 1 female is 3. So the probability of exactly 1 female is going to be 3 out of 8. And that doesn't reduce. Our next question is, what's the probability of having at least 1 male? So at least 1 male. So I'm going to go through and see which ones have at least 1 male. So that one has 1 male, that one has 1 male. In fact, I think all of them are going to have 1 male except the very last one. So the number of having at least 1 male is 7. So the probability of at least 1 male is going to be 7 out of my sample space, 8, and that doesn't reduce. Our next example says, what's the probability of having 4 male children? Well, remember we only have groups of 3, families that have 3 children. So what's the probability of having 4 male children in this sample space? None. There is no outcomes of 4 males. So therefore the probability of 4 males is 0 out of 8, which is just 0, which means it's a complete impossibility of having 4 males when you're selecting a family that only has 3 children. The probability of having fewer than 4 female children. Fewer than 4 female. Well, this one has fewer than 4, this one has fewer than 4. In fact, every single one of them has fewer than 4 females because we only have 3 children again. So the number of fewer than 4 females is 8. So the probability of fewer than 4 females, if we're talking about a family of 3, is going to be 8 out of 8, which is equal to 1, which is a complete certainty. If you are only talking about families with 3 children, what's the probability that you're going to have fewer than 4 female children? 1. It's a complete certainty. You will have fewer than 4 because you're only talking about families of 3.